In 1831, Michael Faraday made a discovery that changed the world forever. He proved that a changing magnetic field can produce an electric current. Every major power source we use today, whether it is coal, nuclear, hydroelectric, or wind energy, still follows this same principle. A magnet moves near a coil, electrons begin to flow, and electricity is created. For nearly 2 centuries, this has been the foundation of power generation. But what if spinning machinery was no longer necessary? What if magnets could create continuous motion on their own? Back in 1937, an engineer working at Ford Motor Company reportedly submitted an internal document describing an unusual magnetic motor prototype. The design used carefully positioned permanent magnets on both the rotor and stator. According to the report, the magnetic attraction and repulsion were arranged in a way that produced constant rotational force, something physicists describe as net torque. Strangely, the report was never released publicly. Inside the company, it was labeled commercially impractical. Yet the idea refused to disappear. Over the last 90 years, engineers from different parts of the world have independently explored similar concepts again and again. That raises an important question. What exactly is a magnetic motor, and why do so many people misunderstand how it works? A traditional electric motor depends on electricity to create movement. It uses electromagnets, coils powered by current, to push and pull a rotor. Once the electricity stops, the motor stops as well. A permanent magnet motor works differently. Instead of relying on external electrical power, it uses the natural force fields of permanent magnets. Most designs use powerful neodymium iron-boron magnets, often called N52 magnets, arranged in very precise geometric patterns. The goal is to create uneven magnetic forces that keep the rotor turning. This is where the debate becomes interesting, because many people misunderstand the physics involved. The first law of thermodynamics states that energy cannot be created or destroyed. Because of that, skeptics often claim a magnetic motor would be impossible, calling it perpetual motion. But a magnetic motor is not truly perpetual motion. Here is the key detail most people overlook. Permanent magnets are not just simple metal objects. They are actually energy storage systems. A neodymium magnet stores energy inside the alignment of its atomic magnetic domains. During manufacturing, the material is heated beyond its Curie temperature and then cooled while exposed to a powerful magnetic field. That process forces the domains into alignment, storing energy inside the magnet itself. An N52 neodymium magnet can hold around 400 kilojoules of magnetic energy per cubic meter. A 1-inch cube contains about 6.5 joules of stored energy. At first, that may not sound impressive. But the remarkable part is how slowly that energy fades. At room temperature, a neodymium magnet loses less than 1% of its magnetic strength over an entire century. That means the stored energy can remain stable for decades. So when a magnetic motor converts magnetic force into rotation, it is not creating free energy from nowhere. It is gradually using the energy already stored in the magnetic domains, transforming magnetic potential energy into motion. In many ways, the process is similar to how a battery converts chemical energy into electricity. The difference is the timescale. A battery may drain within days, months, or years. A strong permanent magnet can maintain its energy for generations. Now comes the most fascinating part. Everything depends on the geometry of the magnetic arrangement. One of the simplest and most discussed designs is known as the Halbach array. In 1980, physicist Klaus Halbach from Lawrence Berkeley National Laboratory introduced a magnetic arrangement that caught the attention of engineers around the world. The concept looked simple, but the results were extraordinary. Imagine placing 5 magnets in a row. Each magnet is rotated 90 degrees compared to the one before it. This specific pattern creates something unusual. The magnetic field becomes extremely strong on one side while almost disappearing on the other. This setup later became known as the Halbach array. Now, here is where things become even more interesting. In a magnetic motor, Halbach arrays can be installed on both the rotor, the spinning section, and the stator, the stationary section. The powerful side of the rotor array faces the powerful side of the stator array. That arrangement creates a magnetic imbalance. As the rotor begins to move, it passes through zones of attraction and repulsion. In a perfectly balanced system, those forces would cancel each other out, causing the rotor to simply rock back and forth without completing full rotation. But the Halbach effect changes the situation completely. Because the magnetic field is concentrated more strongly on one side, the repulsive forces become stronger than the attractive forces. Instead of balancing out, the system produces a continuous push in one direction. That difference creates what physicists call net torque. This is not just a theoretical idea discussed in laboratories. It has been measured in real experiments. Researchers at the University of Technology Sydney tested a Halbach array motor weighing only 2 kilograms. Their setup produced a net torque of 0.3 Newton-meters. That amount of force was enough to spin a small generator and continuously generate around 5 watts of power. At first glance, 5 watts may seem insignificant. But the real story becomes clear when you look deeper into the numbers. A 2-kilogram assembly of neodymium magnets stores roughly 13,000 joules of magnetic energy. If you extracted all that energy instantly at a constant rate of 5 watts, the system would run for only about 43 minutes. Critics often stop their calculations there. But that is not how magnetic systems actually operate. The energy inside the magnets is released extremely slowly. A high-quality neodymium magnet loses less than 1% of its magnetic strength over an entire century. That means the motor is not draining all its stored energy at once. Instead, it continuously draws tiny amounts from a massive long-term energy reserve. When calculated across that timescale, the system could theoretically operate for decades before the magnets would require remagnetization, a process that costs surprisingly little, often around $10. And this is where the story becomes difficult to ignore. Real-world demonstrations have already appeared more than once. In 2004, a Japanese engineering company called Kohei Minato Incorporated introduced a magnetic motor fan that reportedly operated without direct electrical input. The design used carefully machined neodymium magnets mounted on a rotor to drive the fan blades. For 3 years, the company sold commercial units in Japan before suddenly disappearing from public attention. Then, in 2012, engineers in Turkey revealed another prototype, this time a 1-kilowatt magnetic motor connected to a generator. The project immediately sparked controversy, curiosity, and debate among researchers and skeptics alike. The prototype reportedly operated non-stop for 72 hours inside a university laboratory while researchers monitored the test. Later, a peer-reviewed paper published in the Journal of Magnetism and Magnetic Materials claimed the system produced around 1.1 kilowatts of electrical output without any direct electrical input. The results immediately triggered intense debate among engineers, physicists, and skeptics. What surprised many people even more was how simple the construction appeared to be. The basic design starts with a central shaft, usually made from a steel rod. Bearings are mounted on both ends to reduce friction and allow smooth rotation. A rotor disc, often aluminum or acrylic and roughly 12 inches in diameter, is attached to the shaft. Around the edge of that disc, powerful N52 neodymium magnets are fixed in a Halbach pattern. The magnetic orientation follows a repeating sequence: north, east, south, west, then repeats again. Next comes the stator ring, slightly larger than the rotor and built from the same material. Magnets are installed in the opposite pattern so the concentrated magnetic fields face each other. The distance between the rotor and stator is extremely important. The air gap usually needs to stay between 2 and 3 millimeters. If the magnets are placed too close together, they can lock into position. If the gap becomes too large, the magnetic force weakens dramatically. The system also requires an initial push to begin rotating. Unlike traditional electric motors, magnetic motors experience something called carging torque. Certain positions naturally attract the rotor, causing it to settle instead of spinning freely. A small spring mechanism or even a manual spin is enough to move the rotor beyond the first resistance point. Once that happens, the uneven magnetic forces are designed to maintain rotation. The total cost of building a small prototype is surprisingly low. Depending on the size, materials usually range between $45 and $80. Most of the expense comes from the magnets themselves. High-grade N52 neodymium magnets typically cost between $1 and $3 each. A 12-inch rotor may require around 20 magnets, while the stator can need another 24. So why do most electrical engineering textbooks insist that systems like this cannot work? The answer lies in how those systems are usually analyzed. Traditional textbooks focus on perfectly symmetrical magnetic arrangements. In a balanced configuration, the forces cancel each other out, producing zero net torque. That conclusion is supported by Earnshaw's theorem, first published in 1842. The theorem states that static magnetic dipoles cannot create stable levitation or continuous perpetual rotation on their own. But supporters of magnetic motor technology argue that a Halbach array behaves differently because it is not truly static. The rotor is constantly moving through changing magnetic fields. As it rotates, the concentrated flux patterns interact in ways that create dynamic asymmetry, something Earnshaw's original analysis never directly addressed. This is where the discussion becomes even more controversial. Large corporations have invested heavily in permanent magnet motor research for years. Between 2001 and 2019, General Electric reportedly filed dozens of patents connected to advanced permanent magnet motor designs. Siemens filed many more. Supporters argue that companies do not spend millions protecting technology they consider meaningless. That raises another uncomfortable question. If low-cost magnetic systems could produce useful power, what would happen to the global energy industry? The worldwide electricity market generates trillions of dollars every year. Every watt produced independently at home is a watt no longer purchased from centralized power grids. For critics of the current system, that is exactly why small-scale magnetic energy devices continue to attract attention. To them, the idea feels almost unbelievable. A handful of magnets, a simple rotor, and basic materials costing less than a household appliance could challenge an industry worth trillions. And whether the technology ultimately succeeds or fails, that possibility alone is enough to keep the mystery alive.